Hello, I'm Bob Kummerfeld, and this is the second of a series of videos about data representation. This video, the second topic, is all about how we use binary numbers to represent other sorts of numbers. So, the big question is, why do we use binary numbers in computer systems? Why zeros and ones? Well, the answer is that it's very easy to build a switch or a circuit which is either on or off, and we can represent a 0 with an off and a 1 with an on, or a 0 with a voltage present or a not present, or a 1 with the voltage present. So components like transistors are just simple switches, and it's very easy then to use the state of the transistor to represent the 0 or the 1. And so we can build circuit elements that represent zeros and ones, and therefore our computer can work with binary numbers. And the other reason is that we can represent almost anything in terms of a sequence of zeros and ones. And we're going to start talking about this by talking about how we represent numbers. Now, in the previous short presentation, I talked about the binary number system. And this is where we're going to start. So, memory of the computer is all made up of these binary digits, or bits. The word bit is just the contraction of binary digit. However, it's not just a simple stream of bits. It's not just, say, gigabits of data being a stream of individual ones and zeros. Instead, our memory is divided into 8-bit bytes, and these pieces are given a number from 0 to the number of bytes in the memory. Now, you may have a computer that might have 4 gigabytes, 8 gigabytes, 16 gigabytes, or a phone that's got 128 gigabytes or more. And in order to find which particular byte you want to reference, we give them a number, and we call these numbers the memory address. And if you look at the diagram here at the bottom, we've got bytes, the stream of bits divided into these 8-bit bytes, and the addresses above it, 0, 1, 2, 3. So we can pick out a particular byte just by giving the address that refers to that byte. And so on through the memory. Now, as I said, we can represent absolutely everything using patterns of binary digits. We just have to agree on what the patterns mean. So we can represent integers, simple integer numbers, fractions, characters. Of course, I think most information these days is actually that computers work with is actually character strings rather than just numbers. Images, videos, sound. All these things can be represented as bits, and it's just a matter of agreeing on what the representation is that we're using, how to interpret that stream of bits. So, let's look at the first thing, which is numbers. Now, you know from the previous unit that we represented our decimal numbers in binary, just change the base, so that's pretty easy. Of course, it becomes not so easy when we realize that our memory is broken up into these 8-bit bytes, and that puts a limit on the range of values that can be represented. Now, if a byte is 8 bits long, what is the range of values you can represent? Well, obviously, if you start at the beginning and the byte consists of bits that are all 0, so 8 0 bits, then the number it's representing is a 0. Okay, but what's the maximum number it can represent? Well, if we look at the situation where the byte has every bit set to 1, then think about that for a moment. What number does that represent? Well, we know that each position is a power of 2. We add up all our powers of 2, and we end up with the number 255. So in a single byte, we can represent numbers that start at 0 and go up to 255. Now, that's not particularly, well, that is useful, but it's not particularly useful if you want to work with with data, with numbers, because restricting your numbers to have the maximum value of 255 is not particularly useful. And so immediately you can realize that numbers in the computer are not the same as integers in mathematics. Integers in mathematics are infinite. They go from negative infinity to positive infinity. Whereas in the computer, we are restricted by the size of the bit pattern that's going to represent our number. And if we represented all numbers in a single byte, we'd be restricted to the range of values 0 to 255, which is not that useful. Still, let's have a look at a couple of representations. And we did some of this in the previous unit on binary numbers. So if we look at a decimal number, like this 1,00010, what does that mean? Well, you know, each position is a power of 10. But if you were to write out the same number and say that's a binary number, in other words, using a base of 2, then what does that number mean? Well, we convert that to decimal by taking all these powers of 2. We can also represent fractions using binary numbers. And if we agree on where the point goes, in this case we'd call this the binary point, not the decimal point, then it has a similar meaning to what it does in decimal in terms of the powers of the base. So if we take the decimal number 100.010, what does that mean? Well, we apply our powers of 2 on the right side of the dot, of the point, as well as on the left. So on the left, you know that it's 100. Right? It's 1 lot of 100 and 0 lots of 10 and 0 lots of 1. On the right-hand side, it's simply the negative powers of the base. So 0.0 means 0 times 10 to the minus 1. 1, the next 1 means 1 times 10 to the minus 2, and so on. And exactly the same thing applies with binary numbers, except this time we've got powers of 2, or negative 2, to the right of the point, the binary point. So this would be 100, which, if we convert that to decimal, is 4.0. That's 0 times 2 to the minus 1. 1 times 2 to the minus 2, and so on. Now 2 to the minus 2 means a quarter, and then the 0 following that is 0 times 2 to the minus 3. So basically we're representing 4 1/4 here. But if we look at where the point is and follow exactly the same rules of the powers, you can easily work out what this number means. So let's move on. Now, we have to choose, as I said, the representation of your integer or your fraction by choosing how many bits it's going to occupy. And we realize that means it's not infinite. We have to make some sort of assumption. And of course, memory is always finite. You buy a new phone, it's going to have a certain amount of memory. That's how much it's got. You can't fit any more in. Or your PC, same idea. And the PC has two sorts of memory, which we'll get to later in the course. You have memory on the mass storage, the disk storage, and you have memory in the main memory of the computer, which is where the computation is done, and that also has a limit. In each case, it's finite, and we have to choose how big our representations of numbers are going to be. So, the next thing we have to worry about is positive and negative numbers. I've only talked about positive numbers so far, but how do we represent negative numbers in this system? Well, we have to choose some aspect of the binary pattern to indicate that it's negative. Now, we don't have a plus and a minus symbol inside the computer. We've only got ones and zeros. So somehow we have to indicate that it's a minus with a binary pattern or a plus. So usually this is done by some variation on the pattern that's used to represent the positive value. So for example, we could set aside an extra bit, in which case our 8-bit value, if that's all we had for an integer, would chop it down to 7, with the first bit being reserved for the sign bit. And we could decide that a 0 indicated a positive number and a 1 was a negative number. So we could do that. That has an advantage in that it's very simple. It does take away one of our bits, however, and there are many other ways of representing positive and negative numbers, and we'll see some right now. Okay, to explain some of these other number representations that we can use for representing positive and negative numbers, let's introduce something called the number circle. We'll only do it for 4 bits to make it a little bit easier. But let's say we have a 4-bit number and we write the values, the patterns that can be represented around a circle. So here we have on this this slide, we have all the numbers from 0, 0, 0, 0 to 1, 1, 1, 1. In other words, from 0 to 15, and we write them around the circle so that the 1, 1, 1, 1 is immediately followed by the 0, 0, 0, 0 again. So it's just a complete circle. Okay, now that's the number 0 to 15. If you want to represent these as our unsigned interpretation, which is the normal interpretation, here it is with the translation to decimal. So 0 to 15, as I said. But we could also interpret these same bit patterns using another system. And the one I'm going to introduce is something called 2's complement representation of numbers. 2's complement is a way of representing a negative number with some of these same bit patterns and not dedicating one bit as a sign bit, instead using the full pattern. So let's have a look. So if we start at position 0 here, and I've got the base 10 value as well, then you move around the circle. It goes 0, 1, 2, 3, 4, 5, 6, 7. But then the next value, instead of being 8, is -8. And then it counts down, -8, -7, -6, -5, -4, -3, -2, -1, and then we're back to 0. Okay, and this interpretation of the bits is called 2's complement. And the reason it's called 2's complement is that let's say you had a positive number like 1, and you wanted to convert that to the negative equivalent, in other words to -1. The way you would do it is to complement or negate all the bits. In other words, 0, 0, 0, 1 would be replaced by 1, 1, 1, 1. 1, 1, 1, 0, and then add 1. And we get the pattern 1, 1, 1, 1, which if you look at our circle is representation for -1. So that's the pattern. To convert from positive to negative or negative to positive, you take the pattern you've got and complement all the bits. Wherever you see a 0, you put a 1. Wherever you see a 1, you put a 0. And then you add 1 to the result. So let's try it with, say, -2. So we take the -2 pattern here, 1, 1, 1, 0. We negate or complement all the bits, 0, 0, 0, 1. We add 1 to it, and we get 0, 0, 1, 0, which is the value 2. And that's the way the 2's complement representation works. There are some advantages in using this representation for computer arithmetic. It makes the design of the logic for the computer arithmetic a little bit easier. And this representation is by far the most common that's found in computers today. There was a time when the separate sign bit was a popular way of doing it, but these days 2's complement is the most often used representation. Now, let's look at some of the characteristics of this. So while you can refer to that number circle, look at these values. If A is greater than 0 and B is greater than 0, answer this question. Is a plus b always greater than 0? So think about that. Conversely, if a is less than 0 and b is less than 0, is a plus b always less than 0? Now, in each case, if you're talking about mathematics, then that's true. But look, do a few examples from the number circle and see what you end up with, and see if it's also true for 2's complement in 4 bits. Next question, is x squared greater than 0 for all integers x? So take a number on that number circle and square it. Now, we know that you take any number, positive or negative, and you in mathematics, and you square it, you get a positive number. But what happens if we do this for our 4-bit 2's complement numbers? Okay, so once again, you'll find that this is not necessarily true, and it points out, once again, a problem with the finiteness of our representation, that we can't take some of these things for granted. We have to be careful when we do arithmetic, because it may not end up with exactly the result we want, mainly because it overflows the representation. Here's another few examples. Try 5 plus 6. Using the number circle, very easy to do. See what happens. With this one, try minus 2 plus minus 3. Try that and see what you end up with if you're just using the number circle. Right, very easy with the number circle. Count out the 5, then count out 6 more around and see what number you end up with. And once again, the overall lesson here is that number representations in computers are finite. Now, let's go the other way. How big can an integer be? Well, 4 bits gives you only a very limited range. But in practice inside a computer, we use more than 1 byte. We use a sequence of bytes, and therefore a much longer sequence of bits to represent our integers. And the most common length in a modern computer is to use 4-byte integers. Some microcontrollers and other smaller machines might use 2 bytes. But 4 bytes is a very common way of representing an integer. So, first question, how many bits are there in 4 bytes? Well, we know there are 8 bits in each byte, so therefore there are 32 bits in 4 bytes. So that means an integer is 32 bits long. What is the maximum size of an integer that you can represent in our 4 bytes? Well, you can work it out. Take those 4 bytes, or 32 bits, and work out what the powers of 2 are, and you'll come out with a number which is around the 4 billion value. Of course, if we use 2's complement representation to get our positive and negative values, then that will cut down our range considerably, right? In fact, it'll halve it. So there's still a limit. Even though you've now got 32 bits to play with, you've still got a limit on the size of integers. These 4-byte integers are commonly known as single precision integers. In some machines, it has instructions and facilities to handle 8-byte integers, and these are often called double precision integers. They're twice the size. So now let's move on to real numbers. We talked a little bit about fractions before, but now we're going to talk about real numbers. But in mathematics, real numbers can potentially have infinite precision as well as infinite size. So we have to impose some limits in a real machine. And once again, there are many schemes for representing real numbers. So I've shown you one briefly, and that's the idea of a fixed point number. This means that we choose where the binary point is going to be inside our string of binary digits, and we have a fixed number of bits before and after the binary point. So if you look at this number, written in binary, you can work out, using the techniques with before, the powers of 2, you can work out what the equivalent is as a decimal value of that number. But now we get to another very interesting problem. We know these are powers of 2, negative 2 on the right-hand side of the binary point, But there are some numbers that you can't represent in this binary representation. For example, how do you represent a third? Now, the same actually applies for decimal numbers. There are many numbers, of course, that you can't represent in decimal as a decimal number with a decimal point. And once again, a third. The only way you can represent it is by a repeating decimal. So 0.33333, and you simply say, well, that goes on to infinity. Now, of course, inside the computer we don't have infinite bits, and so we, even though it might be a repeating binary pattern, we don't have enough bits to represent the infinite number, so we have to stop it somewhere, and so it's not accurate. It's not exactly a third. So once again, we have limitations on our representation of the numbers. Let me show you another way, and the most common way of representing real numbers in computers today. And that is something called the floating point representation. Now, it's all based around something you're probably very familiar with from school, and that's the scientific notation for numbers. This is where you take a number, like 315.82 in decimal, and you move the decimal point in the number and then multiply the whole thing by the appropriate power of 10. So that you end up with a single digit to the left of the decimal point and multiply it all by a power of 10. So in this case, 315.82 would be 3.1582. Notice we've moved the decimal point 2 places, and so we multiply by 10 to the 2, 10 squared. And that's the scientific notation. Now, there are some technical terms for parts of this. The part on the left, the 3.1582, is known as the mantissa. And the part on the right, or just the 2 actually, is known as the exponent. Right? It's the power of 10 in this case that's going to be used. Now, in computers, we apply exactly the same idea. We have a mantissa and we have an exponent, except this time it's going to be in a string of binary digits. So we break up our string of bits into 3 parts. This time we're not going to use 2's complement for the sign of the whole value. We're going to use a single bit called the sign bit. We're going to have some bits set aside for the exponent because it has to be represented somewhere. And so we choose a small number of bits for that. And then we have some bits for the mantissa. These are the bits which are going to be the real sort of accurate part of the number. And so that's the general pattern. If we look at real computers and real floating point formats, then the one that's most commonly used is a standard called IEEE 754, and it has 3 substandards to it. It's got a single precision format for 32-bit or 4-byte floating point numbers. It's got a double precision, which is 64 bits or 8 bytes, and it's got an extended precision, which is 80 bits or 10 bytes. And if we look at the 32-bit floating point number representation, it starts off with a sign bit, a single bit. Then we have 8 exponent bits and 23 mantissa bits. Now, the 8 exponent bits means that you're able to represent exponents as big as 255. Well, wait a minute, is it? In fact, what they do is they use yet another representation for the sign to represent up to 128 as the exponent, or down to minus 128, actually minus 127. So you can represent a range of exponents there. So you get very big numbers or very small numbers. And the mantissa gives you 23 bits to represent the accurate value of the number. And so this is the single precision 32-bit IEEE standard. Now, once again, there are problems with these representations, with the floating point number representation. And initially, I should say that it's, once again, not possible to represent many numbers perfectly in floating point, just the same as we couldn't represent a third in the fixed point representation. But there's quite serious problems here with doing certain sorts of arithmetic. And unfortunately, many people make mistakes with this when they're doing complex arithmetic inside the computer. They don't take these problems into account, and some sorts of arithmetic expressions that involve large numbers and very small numbers can give you incorrect results or fail completely even. This is usually not a problem and is taken care of by the software, but it's something to watch out for if you're doing very large calculations. Also, repeated operations. For example, if you were to add 0.1 to itself 1,000,000 times, you would gradually lose accuracy. Because of the representation problem, you can't represent things perfectly very often, and every time you do an operation, this is compounded, and so the number gets more and more inaccurate as you go along. Another thing that can cause a problem is the order of operations. You do the operation one way, do the addition, then subtraction, multiplication, whatever, and you do it a different way, and you might come up with different results. And often these differences are only really tiny, but a very common mistake people make is to do two different calculations and compare the results to see if they are the same. Now, very often they may come up with slightly different results, and so you should be very careful testing for equality with floating point numbers. You would normally test within a certain tolerance whether you've got the exact same value. Now, problems with floating point numbers and floating point arithmetic and so on, it's a very big subject, and the whole subject of floating point error analysis could be the subject of an entire university unit of study. So, and in fact, I'm not sure, but possibly there are such units in mathematics. But it's something that you should be aware of, and if you're going to be doing large calculations, you need to look into this. So I've described some of the main methods for representing numbers with patterns of binary digits. There are some other approaches which I won't really spend much time on. For example, if you want to represent really big numbers, way bigger than 32 or even 80 bits, then there are systems which will give you what they call arbitrary precision, and they represent numbers with a variable length string of bits. If you use the Python language, which we will in this course, then it implements arbitrary precision for integers. And so you can have as long a number, or bigger number as you like, and it just simply represents it in more and more bytes. There's also a system for representing real numbers as rational numbers, in other words, fractions. So you can represent numbers using using a pair of integers, and the arithmetic is done using this pair of integers. So that's all I'll say about those two approaches. If you're interested, there's a lot of material available on the web, but we're not going to use them further in this course. So that's all I want to say on representing binary numbers. We'll use them, of course, right through your computing career, but you must be aware that a number is represented somehow as a string of binary digits inside the computer.